much. It's a great pleasure to be here. Back in Japan. It's a very interesting conference. So thanks to the organizer for the hard work, for giving me the opportunity to speak. So I'll be reporting on work in progress that hopefully will appear in the next few months with Chris Beam, Federico Bonetti, and Carlo Meneghetti. There are a couple of distinct lines of work that we're doing with verification as co-authors, and this is building on work that I've done in the past several years with various collaborators, most recently with me. And the general theme of our efforts has been clarifying a remarkable correspondence that we discovered a few years ago between four-dimensional n=2 superconformal field theories, which are complicated, generally interacting quantum field theory in 4 dimensions, and still very rich, but mathematically much better defined work of 2-dimensional chiral algebras, or as mathematicians call them, vector operator algebras. So as I will briefly review, the vertex operator algebra, that is maps associated with 4-dimensional theory, can be understood very physically as a certain closed subalgebra of the full operator algebra of local theory. And it has many uses. For once, given that the vertex operator algebra is generally much more practical, you can often solve certain problems exactly and map them back to 4 dimensions, and thus compute interesting protected quantities that would be difficult to obtain directly in 4 dimensions. But as often the story goes with this kind of correspondences, the map helps in both directions, and so in fact, it's also the case that 4-dimensional physical intuition suggests several new properties and interesting conjectures for the world of vertex operator algebra, some of which have actually been proved. And the more speculative and ambitious reason why we care about this is that this hopefully offers an organizing principle for the whole space of n=2 quantum field theories. The idea being, of course, that given that there's a map, the map, well, we don't necessarily know, the map is certainly injective, we don't think it's surjective, but nevertheless, the map casts a shadow in the simpler world of dimensional chiral algebra, so if we could classify the subset of vertex operator algebra that emerge from 4-dimensional quantum field theory, we would certainly have learned a lot about the list of 4-dimensional quantum field theories. So the vertex operator algebra, by now we have several results, many moving parts. It's hard to really review the story in any depth. It has several interesting features, and clearly the strong flavor one gets if one works on this for a bit is that it is clearly very deeply connected with the geometry and the physics of the Higgs branch of 4-dimensional theories, to be contrasted with what's perhaps the more popular way to attack 4-dimensional theories from the moduli space, which is through their Coulomb branch geometry, which is, of course, cyber-Witten. But the precise connection has so far been somewhat elusive, and in fact today I will report on what I think is finally the general principle that we should hopefully finally connect precisely the physics of this branch with this interesting invariant. So, as I was mentioning, we hope that this may serve as a stepstone towards the classification program, and of course a generic vertex operator algebra is we don't know much about vertex operator algebra. It's a very unwieldy space, but it turns out by experience that the vertex operator algebra that arise from 4-dimensional physics are very, very special. And today I will describe one of really special striking properties that we have observed in all examples that we care to check, and we believe it's general. Namely, they admit free field constructions of their simple quotient. This is somewhat of a rarity in the world of vertex operator algebras, and it means that the null states, the singular states, automatically subtract. You write down in explicit expression the generator to temporal free fields. You compute the singular vector, you see that it's identically zero once algebraically expressed in terms of free fields. And this may sound like a curiosity, but it has actually a very direct physical interpretation. The ingredients, these two-dimensional free fields that enter in this construction, can be recognized in terms of the low energy degrees of freedom that describe the low energy effective action at the generic point of this range. And this gives a strong intuition to search for new such free field construction. In fact, we have never done it. We have a huge list of examples, and given enough investment, we magically always are able to solve it. And so, as I will explain, these free field constructions, far from being isolated curiosities, are in fact deeply connected with the four-dimensional constraints of unitarity, and we hope that this may finally lead to a charting the whole space of vertex operator algebra that arise from four-dimensional quantum mechanics. And of course, given this is a strict math conference, we hope that this will have mathematical influence in their own right, especially with regards to constructing implicit models of the algebra. And we found very useful previous work by Lamovich, and there is a very direct sense in which our examples are past generalizations. Okay, so let me start with some generalities. So we want to study n equal to 2 superconformal theories from the viewpoint of the algebra of local operators, schematic operator power expansion of four-dimensional local operators, generic points R4. And the space of local operators can be organized in representations of the superconformal algebra, which is SU2/4. And I don't expect to offer this information, you haven't seen it before, but I'm mostly interested in setting up notation. So there is a bosonic subalgebra, which is the conformal algebra times the R symmetry algebra, which has an abelian piece SU2R and abelian piece U1R. And what you may want to remember is that the abelian Cartan generator is denoted by capital R, whereas the abelian Cartan generator of the abelian piece is denoted by little r. And so we can label operators by the quantum numbers of the Cartan generators of the superalgebra. And another thing that I want to remember is that E denotes the formal wave. And generically, of course, for an operator that belongs to a generic long representation of the algebra, the operator power expansion is extraordinarily complicated. There is numerical progress in recent years, but we can't do very much yet. But as is often the case with supersymmetry, if you focus on the subsector of shortened representations of the algebra, you can hope to get exact results. And a familiar set of exact results are associated with certain commutative subalgebra that can be still out of the full operator algebra by passing to certain homologies of the Poincaré supercharges. Familiar examples are chiral rings. There's a long chiral ring that is associated with operators that have conformal dimension equal to R. The Higgs chiral ring, which has operator whose dimension is twice instead the non-abelian Cartan big R, and a generalization thereof, which has operator that is conditional. So those will play some role in our story, especially the Higgs and polytopic chiral ring operator. Our story, as I was already mentioning, is really quite orthogonal to the standard Higgs branch. But our story is much richer because we are carving out a non-commutative algebra, which in fact has the structure of a vertex operator algebra. The main trick that I really don't have the time to do in any detail, they were passed to the cohomology not of an ordinary Poincaré supercharge, but of a linear combination of a Poincaré and a conformal. And so now let me very briefly review the basics of vertex operator algebra. You are, of course, very familiar with two-dimensional conformal field theory. talking about a OP algebra of meromorphic objects, where the OP is written this way in terms of integer, in some case half integer, scaling weights hi. And as is familiar, we can expand local operator in Laurent expansion and mode expansion of this kind, and I'm using the physics notation where there's a shift by h. So, for example, famously, if I have an affine current of weight h equal to 1, we'll define the mode expansion by putting a -1 here for the stress center, -2 support and so on. And these modes are operators, so they act on the space of states, and the space of the state itself, in turn, can be identified with the space of local operator, the famous state operator map, hopefully everybody's familiar with, and it simply is a statement of this kind. The nth holomorphic derivative of the operator at the origin is identified with the mode shifted by -n acting on the boundary. So, of course, this is all very informal. It can be hopefully we are on the same page. And a few extra notions that are useful to recall are the notion of normal ordering. In terms of state, we simply put the modes one next to each other acting on the vacuum, and that this can be translated to a statement in terms of normal ordering of operators by the state operator map. And finally, the bracket is defined by picking up the single order pole in the product of operators by this contour integration. The final bit of terminology that we need is the strong generator is an SL2 primary. Of course, there's an action of SL2 by fraction linear transformation on Z as always. And we can identify states which are primary, the center just holomorphic derivatives. And so a generator is a SL2 primary which cannot be written as a normal order product of other things. Okay? So it then follows that the entire state space of the vertex operator algebra can be written by definition as normal order product of the strong generators and of the for example, in the normal algebra, everything is the derivative of D and product of U. I can now describe what is the vertex operator algebra that is associated to a four-dimensional Helicopter superconformal theory by first describing what is the space of states. The space of states are local operators of the 4D theory that obey a certain shortening condition, a certain relation between the quantum numbers, which happens to be this one. And they map to states in the vertex operator algebra whose holomorphic weight h is related in this fashion to the four-dimensional quantum numbers. So special cases of this condition are something that hopefully some of you are familiar with. We recover, for example, the Higgs shortening condition that we saw earlier, or the more generally, the polytable one. But the generic operator is something a little unfamiliar. It belongs to the semi-Schur multiple of the four-dimensional superconformal algebra. It's not something we have much information for. But the key is that generically, if you describe it in terms of a Lagrangian model, it's something which is built, for example, also using holomorphic derivatives, and that's the reason why we have spin among quantum numbers. So the Witten index of the superconformal field theory on S3 is identified, which is also known as the Schur index, is identified with the vacuum character of the vertex. So I've described the state space, and I also need to tell you a little more about how the OP is defined, away from the origin in an R2, which we put coordinates Z and bar inside R4, in order for the operator to be in Q exact, Q close, we need to perform a twisted translation where the Z bar coordinates is accompanied by a shift in the arc symmetry. And in terms of some multiplet of S2R, this means that the operator away from the origin really is a linear combination of things that contains not only the top component, but also lower components in this finite arc symmetry model. And this actually means that the operator product is, so then one shows by homological argument that in fact, although this looks like it has a Z-bar dependence, Z-bar dependence drops out, it's exact. And And so you get meromorphic correlators that define the vertex operator algebra. Now, the point I want to emphasize here, I don't have time to go into the whole story, but the main point I want to emphasize in this equation is that clearly, since the operators are mixtures of different components of the R-symmetry multiplet, they are grading slots. So B does not preserve grading. Nevertheless, it preserves a filtration. Namely, in the operator product expansion of two operators, R can often decrease, but it can never increase. So there's an inequality. So that follows a structural property of vertex operator algebra that descend from Forty theories that somewhere hidden there must be this filtration by R. Nevertheless, if I exhibit the theory abstractly without knowing terms of four dimensions, it's generally impossible to reconcile the filtration. And this is, although it sounds like a technical problem, it's in fact one of the main open problems in the subject, because it's only if we can keep track of all the four-dimensional quantum numbers that we're able to impose the constraints of four-dimensional physics, such as unitarity. So I'll come back to this point, but it's essential. So, so there are some structural properties that I just want to flash. A very curious one is that although this construction is only guaranteed to be covariant under the SL2, the X on Z, in fact, generically, there is an enhancement to the full-fledged Virasoro symmetry, where the central charge is associated to is minus 12, the conformal anomaly coefficient C, and a similar phenomenon happens for affine currents. And you see that because the four-dimensional theory has positive C, the two-dimensional theory necessarily has negative C, so it's unitary, but there still must be some sense in which four-dimensional unitarity imposes interesting constraints on the two-dimensional theory. Now, the property that will be the protagonist of the next part of the talk is this one. I'm going to explain what it means in a minute. It's still conjectural, and it's the statement that the Higgs branch of the four-dimensional superconformal field theory is identified with a quantity that can be intrinsically computed directly in the vertex operator algebra. It's a so-called associative variety of the vertex operator algebra, which was defined by Alcava. This, in particular, means that the associative variety must be symplectic, because the Higgs branch is symplectic. And this has deep consequences that I don't have time to explore today, but you can look at Chris Beam's talk last year's sigma. It implies very curious modular behavior that is quite unexpected from the four dimension. So now let me review Arakawa's definition in my own sort of pedestrian way of the associative variety. So first of all, we define the commutative algebra RP. It's somewhat intricate at first. So we take this operator, the space of states of the theory, and we mod out by this C2V space defined as follows. But really, you can ignore this equation and we can take this in words. To determine RP, we simply remove the states that contain holomorphic derivatives. For example, for an affine correlate algebra, the state space RP is simply spanned by the zero modes, by the mode where we only have J minus 1, because J minus 2 contain a holomorphic derivative and J minus 3 contain two holomorphic derivatives. In other terms, we identify RP with a polynomial ring of the zero modes, little j, a, which are J minus 1 and a on the back. This is a generic level of K, and special values of the level where there are singular vectors, those will infer relations on this polynomial ring. And so now we have a commutative C algebra, and that defines a space, a variety XV by the usual algebraic generalization. So that's associative variety of the vertex algebra. Okay, so let me now describe a simple example, which was in fact done by before us by Adamovich, and I will describe it in my language and generalize it. So I will consider one of the simplest four-dimensional superconformal field theories, which is realized physically by a single D3 brane probing the A1 singularity. So this is a rank 1 superconformal field theory, And the fact that it proves you have a D3 brane that proves a configuration of D7 branes makes it clear that its Higgs branch is the one-is moduli space for, in this case, just SL2. So, more generally, the one-is moduli space for the algebra G is described by the closure of the minimal important orbit, which is the orbit of the group acting on the highest root of the algebra. And so let's be extremely pedestrian. We write an element of SL2, we take the square, and then we impose nilpotency, and that, of course, it tells us that the Higgs branch, also known as the instant moduli space, or in this case, is just C3, spanned by G3, G plus, G minus, divided by the relation that we found by imposing nilpotency. And as is well known, this is just 2. Now, we should also keep track of the holomorphic synthetic structure, which is encoded in these brackets. Now, let's compute, again, in real time, we manage the associative variety of the vertex operator algebra, which is associated with this vertex algebra. Now, it turns out one knows, with variety of consideration, the associative vertex algebra of this interesting order theory is just SL2 at level minus 4 terms. The generator of SL2 are affine current JA, A1 to 3, with the familiar Rastelli expansion. And it turns out that this is a special value of the level from which there is a singular vector at level 3, which I'm writing here, and it generates the whole maximal ideal. And thus, you take the RB space, a generic value of the level, which is just polynomial in 3 variables, J1, J2, J3, and you mod out by this relation, which is induced by the null state. I can easily check that RB contains important elements, because you further contract this with GA, you get something that squares to 0. And so it's not reduced. We need to further mod out by the important elements, but the real radical is just a quadratic Casimir, and so the reduced ring is simply C3 divided by this relation, and so lo and behold, the associative variety is just what we had before. It's 3 divided by this relation, which up to negative variable J plus G1 plus I J2 is okay. So in this example, we have checked our general projection. The Higgs branch is the same as yesterday. Okay, now comes the novel part of the talk. Let's try to reconstruct the vertex algebra by tracing backwards the step that we just did. And so I start from the geometry, and I want to uplift it to an affine. So I start with the geometry, which is this one again, and then in an open patch where say J plus is different from 0, I can just solve for J minus, and then this symplectic structure is just encoded in this bracket. And then I want to convert the little j's to big J's, which are affine currents. And I do that by, I start with a 2-dimensional space, so naturally that suggests that I should take 2 chiral bosons, and you can check that if you make these definitions, then the OP of these objects has a single order pole that is the counterpart of this bracket. The Poisson structure gets uplifted to an affine structure of this kind. And then the statement that J class with J class has 0 brackets is a statement J class with J class should have regular OP, and that forces this lattice of bosons delta and phi to have opposite norm. And finally, the hardest step is to consider J minus. J minus, you see, was something we had written as the inversion as 1 over J plus. So given that J plus has an exponential with plus signs, we naturally guess that J minus is an exponential with minus signs. Okay? Take an answer of this form, and then you close all the OPs, and everything works if and only if K is quantized to one of these 3 values. And in particular, we recover the value minus 4 terms. So this is not our construction. This is work by Adamovich. And what's quite remarkable about it is that all singular vectors are automatically removed. Okay, you may be familiar with the Bakimoto construction for SL2 at the generic level that uses 3 bosons. And if you find this special value of the Lepper, I'm using only two bosons. It's not a coincidence, it's just a dimension of the Higgs branch. And then the nulls are automatic. Okay, great. So what is the physical interpretation? The free field construction mimics the effective field theory description at genetic quantum Higgs branch. So in this superconformal field theory, at low energy, we have something extremely simple. We have a single free hypermultiple. Or two half-hyperts, and two half-hyperts are what precisely gives rise to two chiral bosons phi and delta. So now we need to generalize the example, but now we have exactly the key to all generalization, which is look at the effective action and the effective description of the Higgs branch. And so we can generalize the story in many directions. We can still look at the effective field theory that only contains hyperts, but with a more complicated geometry. Or perhaps we could look at examples where there are free fields that correspond to unbroken one gauge groups, so those give rise to light vector multiplets. And finally, the more delicate example is when some interacting superconformal theory survives at low energy. So in addition to the fields, we have some remaining superconformal field theory which better have trivial Higgs branch, because if we observe the genetic quantum Higgs branch, there is no Higgs branch to be had. But nevertheless, there may be still some interesting irreducible quantum fields with no geometry. Okay, so these are the three classes of examples I want to discuss. So the example with pure hypermultiplets, so the most beautiful class of examples is this sequence of a fine current algebra that appear already in Harvey's talk. So this peculiar list of Lie algebras, which is known as the Deligne-Cvitanović series. But whereas in his talk he was considering them at the unitary case or level 1, for me it's essential that they are at this special non-unitary value, related in this fashion to the dual constant number HB. Now the four-dimensional interpretation of G2 and F4 is still rather unclear, but the others are familiar. These are vertex operator algebra associated to the rank 1 superconformal field theory that arise on a single D3 brane probing the corresponding singularity. And again, the F theory description makes it clear the Higgs branch is the one incident moduli space, or again, the closure of the minimal important orbit, which is the G orbit of the highest root. And Arakawa and Moreau had independent previously computed the associative variety, and thankfully it agrees with what we need. Okay, so now how are we going to construct the free field representation where we use physical intuition or geometric intuition, which in this case are sort of the same. We move the generic point of the Higgs branch, and that, because the Higgs branch is the minimal important orbit, that means that we need to give a path to a moment map that corresponds to the highest of the adjoining. And so we define the SL2 triples associated with the highest root. And in physics parlance, then, once we move on the Higgs branch, we're going to have quantum bosons and broken generators. And so we decompose the algebra in this fashion. So G natural is a commutant of this SL2 triple. And then the rest of the algebra will decompose into some representation R of the commutant, which transforms, as it turns out, as a doublet in a half of this SL2. Or I can also exhibit the grading more explicitly. There is the lowest root F theta, which has kaptan minus 1 under kaptan H, then R minus, which has kaptan minus a half, the zero kaptan space, which is the commutant, and H theta itself, R plus, which has kaptan plus half, and finally the highest root, which has kaptan plus 1. So you can go through the exercise of computing the representations for these interesting Lie algebra. Here they are. And so the broken generators are easily enumerated. It's F theta, H theta, and R minus, so you can count their dimension and have, thankfully, degrees with what we need for the dimension of the minimum control. Now, R is a pseudo-real representation of this dimension, and you can think of it and recognize that the commutant is, in fact, a subalgebra of the symplectic algebra of dimension. And so now we know what we should do. We should introduce bosons. We should introduce bosons that describe the SN2 triples. But now we need additional degrees of freedom for this additional bosons from the indexing representation. And for that, it's very natural to use a system of symplectic bosons. Remember, because the representation was pseudo-real, so there is a natural symplectic form. We identify the cartan of the H triple with del phi. The commutant is realized in the appropriate fashion as a subalgebra of a symplectic algebra. And then the highest way could not be simpler. They take this very simple form. You see that the symplectic boson has dimension and a half. This gadget has dimension and a half. All in all, it's 1. This gadget has dimension 1. And what takes some work, in fact, it's not work, and how to collaborate with mathematical packages, is a construction of the lowest weights. But when the dust settles, you see that you can now write it in a nice way by isolating a red object, T natural, which is just made of a symplectic boson, and it's claimed to claim that it commutes with G hat natural, and you play this game, and you need to have mass. So I cannot write the expression because they're a little complicated, but it all works. So again, this is a free field construction of a simple function, which is out of calculus. And just check that all the null states are mathematical. And in this case, it's rather easy to check because Arakawa and Moro told us that the maximal ideal is just generated by a level of singular vector, just to check that those are zero. And again, interpretation I've already mentioned. In this case, the low energy degrees of freedom are just a bunch of free hyperts, which in this case, to start with the thing which has this large symmetry, the low energy degrees are just a Goldstone mode property. In more general situations, at low energy the Higgs branch will have like hyperts, but they will not be Goldstone mode. In this case, and in fact, you can, from this viewpoint, you can also understand why these Goldstone modes have shifted symmetry. It starts 1 in the UV and becomes 1 half in the infrared, because you need to redefine the R charge to have arcs in the infrared. Okay, the second class of examples is what I mentioned already. We want to consider theories that at low energy have unbroken vector matrices, have light vector matrices. And the canonical example is, of course, any components by Mills. So let's take any components by Mills with gauge algebra G, and then this is the Higgs branch in a perhaps slightly over sophisticated way, but it's you take R to the rank of the algebra and you mod out, you complexify times C2 because that's a Higgs branch, and you put out by the value group. And as we know, at a generic point there will be U1 to the rank. Now, it turns out that we worked out the associated vertex operator algebra some time ago in a somewhat decent fashion, I must say. But we recognize that it was a super W algebra that contains, as a subalgebra, a small n equal to 4 super Pirozoro algebra. And beside the super Pirozoro generator, there are additional song generators that include, among other things, one short super primary for each fundamental invariant value. Okay, those are things that descend from the generator 1/2 BPS Higgs chiral ring in 4 dimensions. So let's look at the simplest case, which is, of course, SU2. And then the associated vertex operator algebra is simply the n equal to 4 super Pirozoro algebra at a very peculiar value of the central charge, -9. The Higgs branch is, of course, just C2 mod Z2, which is the same Higgs branch that we had before. But you see, now there's an important twist. The generic point of the Higgs branch, you don't just have 3 hybrids, you also have 3 vectors. And that changes your low energy description, that changes your realization. And so, to account for the unbroken U1, we must include fermionic fields. That comes from our previous diction that I didn't have time to review, but it turns out that vector multiplets are associated to fermionic free fields. And in terms of those, you representation because you utilize them to construct the correction dimensional that you need for the lowest generator. So it has to be that there needs to be a correction, because I just showed to you before that if I just want to construct SL2 and I don't add a correction, the only possibility at level minus 4/3, minus a half, and minus 2, but the level of the SL2 subalgebra, which is labeled subalgebra in this case, is minus 3/2. So the correction is nicely given by the fermionic fields, which correspond to vector multiples. Now, I didn't write down explicit formulas, but it all works, and this is in fact closely related by some theory definition to another construction of Adamovich, which where the connection with Higgsing is less obvious, but it's perhaps more compact, and it's in terms of two first-order systems, a beta-gamma system of weights 1, 0, and a BC system of weights 3/2 minus 1/2. And the generators are written, the highest weight generator are written in extremely simple fashion. In this way, for example, G plus is just beta, and G plus is just beta. And then, sure enough, with work and powerful collaborators, you can generalize everything. And so we generalize this to all gauge algebras. And the latter construction is the one that generalizes most easily. For general G, you use rank G pairs of beta-gamma BC system of weights P over 2 and P plus 1 over 2, where P are the degrees of the fundamental invariant, which I have reviewed here. Now, the curious thing is that you find the list of the algebras, but then we were not content with that. We added the non-crystallographic constant groups, and for reasons which are not entirely clear to me, the construction goes through. So we're able to construct vertex algebra with n equal to 4 superconformal symmetry that correspond to exotic non-crystallographic Coxeter groups, the four-dimensional interpretation of which is, of course, very unclear. Anyway, this gives you basically a complete construction of the super W algebra associated to n equal to 4 super Yang-Mills. Truth be told, we didn't carry it out completely, so the story gets complicated when you have to construct explicitly the lowest weights. The highest weights are automatic. The lowest weights are complicated. So we have several very explicit constructions in many examples, and one particular uniform example that works very well is this non-crystallographic I to T case, and then lower rank cases are also very explicit, and in some sense this is the first true construction of these algebras that before were only known in a somewhat implicit fashion. I must say that even in the previous examples, the construction really works rather miraculously. You construct this lowest weight by acting with the generators, and then all the second-order Boltzmanns vanish, and they do always in a rather surprising and miraculous way. Now, the third and final class of examples I want to discuss are theories that have a residual interacting superconformal theory at the generic point of the Higgs branch. And the simplest examples are this infinite sequence of Argyres-Douglas theories, whose associated vertex operator algebra turns out to be again SL2, but a different fractional and in fact admissible value of the level. For each n, the Higgs branch is still the same. So it's clear that if you want to construct the algebras, you need to introduce some additional ingredient, because it cannot be just made purely in terms of geometry. The geometry is always the same. And the additional ingredient is the statement that if you sit at the generic point of the Higgs branch for n greater than 1, n equal to 1 is the case of SL2 level minus 4/3 that I studied in detail before, the effective description on the Higgs branch must include an interacting irreducible quantum piece, which happens to be another Argyres-Douglas theory labeled by this pair of the algebras. And the vertex algebra of this theory is just a Virasoro algebra, and this famous sequence of non-unitary Virasoro models, of which the first interesting one is 2,5 to 3 Young. And then you predict from physics and condition that we should be able to construct this vertex algebra in terms, again, of our old friend chiral boson delta phi plus an additional Stratt-Virasoro algebra of this type that should provide the needed correction term in Schur. And in fact, we found in the literature precisely such a construction, again, by Adamovich. So I decided to present here many examples that were already known before, but because I'm the simplest. But in fact, there's a basically you can play this game forever. Okay, so any example that we care to look at, given sufficient work, appears to always have a solution. And so there are Lagrangian theories, infinite sequences of algebras, Laplace theories, class S theories. And one way to understand what has been achieved here is an inversion of Deligne-Cvitanović reduction. Okay, so the standard DS reduction imposes a quantum constraint where a negative root is set to 1 for an affine current possibly subalgebra of the full vertex operator algebra. And those are this kind of constructions what he describes, all the examples that I described today in detail. But in fact, we have also found examples where what is being inverted is a more general kind of reduction, where the operators that were set to 1 are not affine currents. And the cute example is super QCD, SUN, gauge theory with 2n fundamental hypers, and then the operators that need to set to 1 are variants. This is some sort of unknown variant, like this unknown to me before the S reduction, and we are able to invert and give free field description. Okay, so this may sound all a bit esoteric and a bit of collection of curiosities, but in fact, for us, this is really the key insight to what this whole structure means, because, among other things, we are finally able to recover experimentally this lost R-filtration that doesn't appear to be intrinsic to the vertex operator algebra, but now that we have the free field construction, we can in fact define. And so, for example, for n for Mills, we assign these quantum numbers to the elemental levels, and then we declare that the polynomial has weight equal to the maximum weight of its monomials. And with this assignment, it turns out this really does correspond to the R-symmetry filtration, and we recover this more general superconformal integral that keeps track of the big R quantum number, which is known as the This is all experimental, but it's true in all the examples that we checked. And so the R-filtration is crucial because now that we have it, we can impose the conditions of, for example, positivity of square root coefficient that comes from 4 dimensions. And so the emerging picture, let me reiterate, in all examples that we checked, and we believe this is general, the vertex operator algebra associated to 4-dimensional superconformal field theory can be sort of reconstructed in terms of building blocks, which may include, in some cases, irreducible quantum pieces that have no Higgs branch. If they have no Higgs branch, they must correspond to vertex algebra with no associated variety, and by definition, those are so-called C2 cofinite. And then free fields, which may be either of free hyper type or free vector type. And I believe that, in fact, this is forced upon you, very abstract, just by the requirement that there has to be an R-filtration and the structure to be compared with 4-dimensional type. And in fact, we are beginning to see that even these irreducible C2 cofinite blocks are a bit of a nuisance because you can't really look inside the black box, are in fact extremely constrained from 4-dimensional unitarity. And so there's preliminary evidence, in fact, that if you assume that the full vertex operator algebra is just Virasoro, this forces you to the list of theories I had earlier. In particular, C2 cofinite comes from 3. So in this case, it would be actually a proof of the conjecture that the associated variety is the Higgs branch. And so hopefully this is the beginning of a way to, first of all, distill the axioms that define the vertex operator algebra that can arise from 4-dimensional superconformal field theories, and then perhaps didn't mention at all, what this may be good for is studying representations. The physical interpretation of modules of vertex algebra is the insertion of surface defects localized at point and algebra range for dimensions. And what this story is telling us is there are special representations. There's a finite set of very well-made representations in category O, and they should correspond to a particular nice set of surface defects, and making the picture precise would be very interesting. Thank you.